Okay, so let's dig in a little bit to this idea of asymptotic variance, which I mentioned. We know that these a lot of estimators are asymptotically normal, and we also saw that as we increase the sample size. So here I've actually fixed the x-axis to be on the same scale. So you can see that as I increase the sample size, my variance starts to get smaller and smaller and smaller because more samples means more precision in estimation. And this is formalized in the central limit theorem. The question is, okay, well, how are these things all related, right? And so I showed you this slide here that I can write this as, I can just bring this sigma star root n out and say that approaches a constant. So that's kind of what I'm going to do now. I'm going to say, instead of showing this distribution, the sampling distribution of my estimator, which will have shrinking variance, this is the way that it's shrinking. I can say, okay, well, what is this kind of constant here? If this is shrinking, what is the constant that is what we call the asymptotic variance? So in this case, by plotting it, I'm just kind of saying, okay, this is like in this case, this constant is like 3.5. And so the variance of my estimator at any given sample size is going to be different, but I know it depends on some number divided by n, and so that number is what we call the asymptotic variance. And it's another way of putting it is like if to get the variance of our estimator at a given n, we just need to divide that number by this asymptotic variance by n. And so if we scale our estimate by root n and plot the sampling distribution of that, this thing is a constant. You can see it's not shrinking in. The variance of that is not shrinking in. And the variance of this is what we call the asymptotic variance, which I can use this little sigma star or sigma infinity to denote that. And this is the asymptotic variance of this estimator. And it doesn't depend on n. This is the nice thing about that is it doesn't depend on n. It's just some constant. And you can get for a given sample size what the variance of this is if we know this number, because we just divide by n. Which is exactly what I'm showing here. This is the main message. To get the standard deviation at a given sample size, you get the asymptotic standard error, and you divide by root n. Or alternatively, to get the variance at a given sample size, you get the asymptotic variance if you could know it, and you divide that by root n. Of course, we don't know that number, right? We don't know the asymptotic variance in practice, but what we're going to see is that's a number that we can characterize analytically and then estimate it. So that'll be kind of the subject of the next lecture. So let me actually just show you what I'm doing here in R really quick. For those who are curious, I'm just going to put this thing. So here I was getting the sampling distribution. For a given sample size. Okay. And now I'm just going to repeat this whole thing, looping over the sample size. So I'm going to try sample size of, say, 5, 10, 50, 100. I'm just going to say, what n is that from? See if this works. Okay, so it's giving me actually like 4 different data frames. So I'm I'm going to make them, this will just make it so that they're all glued together. Again, the details of the code here is not important. I'm just showing you that I'm going to plot all the sampling distributions simultaneously for different n. No. Okay, great. Here we go. So sampling distribution when n equals 5, 10, 50, 100. So you can see it's narrowing in, like we said. However, if I multiply all of the estimates by square root n, now we can see it's stable, right? So it's not, so I've kind of just blown them up or shrunk them all by the right number, which happens to be square root n, so that they're kind of stable. And now I can look at what's the variance of this, and that's what we call our asymptotic variance or asymptotic standard error. Take the square root of that. Okay, so those ideas may be a little difficult to grasp. What is asymptotic versus non-asymptotic standard error? The main thing to understand is this picture, okay? That the sampling distribution of your estimator gets more normal with bigger n, and not only more normal, but more precise. So it gets more clustered around the true value for a sample mean. And that this extends to many, many, many other estimators. And that the reason we care about that is because that helps us characterize the bias on the variance. Because all we need to know is what's the expected value of our estimate and what is the variance. That tells us everything about the sampling distribution that we need to know. That we'll see in the next lecture why that helps us produce some very interpretable measures of the uncertainty that in our estimate, namely a confidence interval and a p-value. So we now have the tools to describe those things concretely and tell you how to actually build them, given an estimator. So we'll see you there. These are very, very important ideas. The most important idea in statistics, basically the only idea in statistics, is that your estimate is random. Okay, so keep that in mind, and we will see you next week.